In this video, I will present a very important and useful theorem about continuity. It is so useful that you have probably already used it, even if you had not realized it. As a reminder, here is the definition of continuity. A function f is continuous at a point when calculating the limit is the same as evaluating. Not all functions are continuous everywhere. If they were, computing limits could be much easier. But a lot of common functions are continuous, and that is what this theorem says. Specifically, any function we can construct with sum, product, quotient, and composition of polynomials, roots, trigonometric functions, exponentials, logarithms, and absolute values is continuous on its domain. That is a lot of functions, and they are the functions we use most often. Sometimes these functions are called elementary functions. Elementary does not mean easy, it is just the name for this class. For example, how do we compute the limit as x approaches 1 of this ugly-looking function? As complex as the function may look, it is in the class of functions in the theorem, so it is continuous. 1 is certainly on its domain, so to compute the limit, I simply plug in x equals 1. That's it. Nice. An important warning. The theorem only applies to these functions on their domain, so not all limits involving these functions are a matter of plugging the value. For example, the function f of x equals sine of x over x is not continuous at x equals 0 because 0 is not in the domain. If I wanted to compute its limit as x approaches 0, I could not simply evaluate. Or the function tangent is not continuous at x equals pi over 2 because pi over 2 is not in the domain. But still, this theorem is extremely useful. It is worth proving it. Of course, I cannot prove it for all functions one by one. Instead, I have a better plan. The plan goes in 2 steps. Step 1. I need to prove that the basic functions are continuous. The basic functions are the building blocks that I use to construct other functions. I have chosen 6 basic functions. Constant functions, the function f of x equals x, basic exponential, natural logarithm, sine, and absolute value. Step 2. I need to prove that the sum, product, quotient, or composition of continuous functions is continuous. And that will be it. Perhaps you think that I forgot some basic functions, but I didn't. These are enough. Other functions that we might have considered basic can be built from these ones. For example, cosine can be written as the composition of a sine and a polynomial. Or tangent can be written as the quotient of sine and cosine. What about exponentials with other bases? Or square roots? They can both be written as the composition of e to the x and other functions. Okay then, we need to take these 2 steps. I am not going to prove that the 6 basic functions are continuous. I hope I have persuaded you that I have simplified the problem enough by reducing it to only 6. They can be done, some are easier than others, but I will not write those proofs for now. What about step 2? Use the limit laws. For example, I will prove that the sum of continuous functions is continuous. Let f and g be 2 continuous functions at a. By definition, that means that their limits as x approaches a are simply f of a and g of a. Then the limit law for sums tells me that the limit of f plus g will be the sum of the limits, f of a plus g of a. But by definition, this means that f plus g is continuous at a, and that completes the proof. That's it. That was easy. And the exact same argument will work for the product and the quotient of continuous functions using the corresponding limit laws. Then what is left to prove? We still need to prove that the composition of continuous functions is continuous. The problem is that we do not have a limit law for composition. That is an interesting problem on its own, and it is the topic of the next video. In it, I will explain why there isn't a limit law for composition, but nevertheless, composition of continuous functions is still continuous.